Okay, hi. Today I'll be presenting a joint work with Ayelet Tal and Lihi Zelnik-Manor, titled OTC, a Novel Local Descriptor for Scene Classification. So what is scene classification? Scene classification is the task of determining the scene in which a photograph was taken. So for instance, here you can see a photograph that was taken outside of a fire station, of a badminton court, inside a limo, or even being able to differentiate between a power plant and a nuclear power plant. Looking at recent work, we noted a couple of things. The most work focused on either mid-level representations, such as spatial pyramid matching, Fisher vectors, and so forth, or high-level features and learning paradigms, such as hierarchical learning, contextual, or incorporating contextual and semantic cues, and deep learning frameworks that learn the features themselves. The other thing that we noted is that most feature-based solutions use off-the-shelf local pattern descriptors, such as HOG and SIFT. And while these descriptors have been shown to provide good results for other tasks, such as object detection, they're not necessarily best suited for the task of scene classification. And this led us to examine whether a more suited descriptor could be constructed. So our contributions are twofold. First, we propose a local pattern descriptor for scene classification named Oriented Texture Curves, or OTC for short, that outperforms the previously best descriptor by over 7%. Furthermore, we showed that by combining our OTC descriptor with a HOG descriptor in a very simplistic framework, we are able to outperform the best feature-based algorithm that uses 14 different descriptors and just falls shy of the most recent deep learning algorithm. I will now go over the construction of the OTC descriptor. So in constructing a more suited descriptor for scene classification, we began by identifying a couple of desired properties for descriptors for such a task. I will go over each of these properties as we construct the descriptor. The first being the property of being rotationally sensitive. So looking at various photographs taken of various scenes, we noted that most scenes are taken right side up. Therefore, having a descriptor that is rotationally invariant is not very helpful. Furthermore, we know that orientations can actually help us in classifying the scene. Here you can see two patches taken from the image, one from the white picket fence, the purple patch, and one from the house, the orange patch. You will note that both patterns are highly similar, but they differ in their orientations. And being able to pick up on those differences, we are able to pick up on cues such as the white picket fence, which is very beneficial in being able to classify suburban scenes. And lastly, looking at the results of rotationally sensitive descriptors versus rotationally invariant descriptors, we see that rotationally sensitive descriptors outperform the rotationally invariant descriptors, as you can see here by comparing the SIFT and HOG descriptors. Here you can see two different patches taken from the image. Both patches are taken from the white picket fence. Both patches are highly similar. Therefore, we would like our descriptors to be highly similar as well. Bearing in mind that different features are dominant in different orientations, we scan the patch in 8 predefined orientations. Each time, we average the pixels along the line and scan the line in the appropriate direction. You can see that this orientation indeed captures the features within the patch. Looking at the orange orientation, scanned top to bottom, we note that since the pattern does not change along this orientation, we get two flat curves. But looking at the green orientation, scanned left to right, you can see that we indeed captured the features within the patch. Still, this representation suffers from a couple of issues. The first one is what we call the illumination problem. You can see here that while, as expected, both curves have a similar shape. But due to the difference in the local mean between the two patches, we can see a gap generated between the two curves. If we were to take the difference between the two curves, we would get an unwanted large difference. Furthermore, this representation is also sensitive to geometric distortions. Here you can see that in the red patch, the left fence post is thinner than in the blue patch. Therefore, you can see that the red curve drops sooner than the blue curve. Again, if we were to take the difference between the two curves, we would again get a large unwanted difference. So dealing with the first problem of what we call the illumination problem, instead of using the representation I showed before, we look at the shape of the curve itself, which can be described by its gradient and curvature. We approximate the gradient curvature by the curve's first and second derivative. And you can see here that this representation indeed solves the illumination problems, and you can see that the red and blue curve look highly similar. Still, this representation does not solve the issue of the geometric distortion. And you can see that by looking at the green orientation, and you can see that in both the first and second derivatives, the gap between the red and blue curve is still apparent. To solve the geometric distortions, a couple of solutions have been proposed. The first is using some intelligent or smart distance measure, such as dynamic warping, that will find the best match between two descriptors. The problem with this approach is its high computational complexity and its compatibility with common methods such as k-means, since it may be difficult to define the cluster's centroids. Another popular method is using orderless representations such as histograms. The problem with using histograms is the well-known quantization error, which can be elevated to some extent using soft binning. Instead, we use a novel orderless representation. Here you can see two descriptors, the blue and the red descriptors or vectors. In green, you can see their L1 difference. To find the best match between the values of the descriptors, what we do is we simply sort each of the descriptors independently. The obtained matching between the two vectors is now guaranteed to give us the minimal L1 distance between the two vectors. Of course, this method does not suffer from high computational complexity. It's compatible with common methods, and there's no problem with quantization errors. So coming back to our example, given the first and second derivative of a certain orientation, all we do is we just sort their values. And now you can see that the generated red and blue curves look highly similar. Therefore, this shows us that we have overcome the geometric distortion problem. So our descriptor so far is just the concatenation of the sorted first and second derivatives of each of the orientations. And of course, you can see that it is rotationally sensitive since we scan the patch in predefined orientations. It's robust to illuminations since we use the first and second derivative to describe the curve. It's robust also to geometric distortions since we find the best match between the vectors using the sorting operator. Still, we have still to normalize our descriptor. The problem with using current normalization schemes is that they may produce false features. And you can see that in the example below. Here you can see a descriptor of a textured patch, which contains information. Here you can see in blue the descriptor of a textureless patch, which contains mostly noise. And the reason for that is because our descriptor is texture-oriented. Surprisingly, after applying L2 normalization to both descriptors, we get the exact same values. So to avoid this creation of false features, what we do is a very, very simplistic approach. We just add a very small constant bin, which we call the H bin, as in homogeneous bin, before normalization. And you can see in the red example, the bottom row, that when normalizing a textured patch, the small constant bin hardly affects the normalized values. But looking at the textureless patch, you can see that we avoided the creation of false features and most of the energy concentrated in the H bin. And you can look at the H bin as a sort of indicator of homogeneity. Here you can see an example where we densely sampled the image, computed an OTC descriptor, added the H bin, and applied an L2 normalization. On the right side, you can see the value of the H bin after normalization. You will note that in homogeneous areas, indeed, the H bin received a high value, and in textured areas, such as the house and the tree, the H bin received a low value. So basically, our OTC descriptor is just a concatenation of the H bin and the OTC no norm after applying the L2 normalization. And of course, as we saw before, it's rotationally sensitive, it's robust to illumination, it's robust to geometric distortions, and of course, it avoids the creation of false features. Next, I'll show how we incorporate our OTC descriptor in a scene classification framework. So we begin by densely sampling the image and computing our OTC descriptors. We then cluster those descriptors into 1,000 words. For each image, we then apply a 3-level spatial pyramid pooling, which we then classify using a one versus all SVM. And we examined our results on the most extensive data set to date, the Sun 397, which surprisingly contains 397 scenes, both indoor and outdoor. It contains over 100,000 images, ranging and is highly diverse, ranging from elevator shafts to tree houses. And here you can see the results. In green, you can see the exact framework I described earlier using our OTC descriptor. And you can first note that we outperform previous descriptors using the same framework. Furthermore, you can see that we even outperform more complex algorithms that use hierarchical-based learning and incorporate semantic context. In purple, you can see a combination of our OTC and Hog descriptor in the same framework I described earlier. And you can see now that it outperforms the best feature-based solution that uses 14 different descriptors, and even outperforms the decaf algorithm that uses deep learning, a deep learning framework, and just falls shy of the most recent deep learning framework, MOP-CNN. Still, since we use a very simplistic framework, we believe that if you would replace the SIFT and Hog descriptors in more complex algorithms, you would get even better results. So here you can see a couple of our misclassifications. Since our descriptor is texture-based, scenes that share a similar texture sometimes get confused. Here you can see such an example. The bookstore and the fire escape both contain strong horizontal and vertical patterns. Therefore, they were sometimes misclassified. Here you can see another example of common misclassification between scenes that differ mostly in their semantic context, such as the pasture and the racecourse. Looking at the confusion matrix of the first hierarchy level of the Sun 397 dataset, you can see that indeed most misclassifications occur between scenes of a similar texture, such as outdoor man-made and indoor, or between semantic differences such as outdoor nature and outdoor man-made. When comparing our performance on this hierarchy level to that of a recent hierarchy-based learning framework, you can see that our simplistic framework produces state-of-the-art results. This is the confusion matrix on the second hierarchy. Again, you can see that most misclassifications occur between classes of a similar texture, such as mountain sky and water, ice, and snow, or classes with semantic differences, such as workplace and home and hotel. Again, you can see that we outperform the ML-DDL algorithm that uses hierarchical-based learning framework. In a recent paper titled Hoggles, the authors examined the reason for false positive detections by visualizing the information captured by the Hog descriptor. They did so by learning the transformation between feature space and image space. Here you can see such an example where a car was hallucinated in the water. Using their framework, we examined our performance using our OTC descriptor. And you can see that indeed our descriptor is more robust and it avoids the creation of false features and therefore hallucinations. In conclusion, we presented a local pattern descriptor that uses a novel sorted representation and a smart normalization scheme that avoids the creation of false features. We showed that its performance in the task of scene classification provides state-of-the-art results when combining with the Hog descriptor. And lastly, we believe that OTC descriptor can replace the Hog descriptor in other tasks as well that rely on rotationally sensitive descriptors. Thank you.